So the laws of physics as developed or authored by an physicist can be of two types. Physical law. Now this can be a theoretical law and another type of law is the empirical law. When a physicist evolves a theoretical law, he just uses his intuition and educated guesswork to formulate a law. He has not observed the phenomena around him, he just thinks, and the thinking process has to be not like a layman but of a person who is educated, who has done a lot of studies, and that's why this is called educated guesswork and intuition. By that he formulates a law. Let me give an example. So when Newton developed the law that force is equal to mass into acceleration, it's very difficult to experiment that and find exactly this in daily experiences because friction is a very important force on rough surfaces. So he had predicted that if friction could be withdrawn and a body could be acted upon by a force, you would have an acceleration given by this formula. Now this is guesswork, this is intuitive knowledge. He develops the whole theory of laws of motion, and when it's applied in ideal circumstances, it is found that experimental results and observations corroborate this law. Now that is a theoretical law based on the intuition and guesswork of a scientist. On the other hand, there is something called empirical law, as you can see. Now these laws are evolved in a different way, the other way around. The physicist does a lot of experiments, he observes and collects data, and then he tries to construct a law that fits very well with those data observed by him. So in theoretical law, first comes the theory that's developed on the basis of the scientist's intuitive knowledge, his intelligence, and the guesswork. And empirical, on the other hand, it is first done by experiment, data collected, analyzed, and then we try to evolve a law that corroborates the experimental results in the best possible way. It might happen that certain data will not really corroborate this law, there may be some aberrations, but mostly in most cases it's found that the data from experiments and observations, they fit the law that was constructed on the basis of that data later. Now that is an empirical law. Now both these types of laws, you are aware, they go to explain the phenomena around us in the universe, and so the job of a physicist is clear cut. His job is to formulate a theory and a law either theoretically or empirically, and to see that the phenomena around him that he first didn't understand, he can explain them with the help of those laws and can even predict what might happen in future in a certain given circumstances. Now that's physicist's job in physics. So one thing I like to tell you about the laws. Now the laws that have been in vogue, they're in practice for many decades or maybe even hundreds of years, centuries. It is not that the laws are sacrosanct. Physics laws, there is no such rule that once it's accepted by scientific community, these laws will always remain valid and there will be no aberration in that. It's not that true. Let me take an example. Let me give an example of empirical law as well. See, the laws of Kepler, Johannes Kepler, a German scientist, he evolved the laws of planetary motion. Now these laws of Kepler of planetary motion were developed on the basis of experimental data by himself and his predecessor. His name is Tycho Brahe. He was a Danish astronomer. And there are three laws of Kepler developed in the very beginning of 17th century, in 1610s, in that decade. So one of the laws says that, this is Newton's law I have written down. This Newton's law is of course a theoretical law, and this law was evolved on the basis of Newton's thinking and intuition. But let us compare that with Kepler's one of the laws, that is the law of periods. It says that the time period of a revolution of a planet around the sun, square of that, varies as the cube of the radius of the orbit of the planet around the Sun, assuming the orbit to be approximately circular. So this particular law, which says that square of time period of a planet proportional to the cube of average radius of the orbit of the planet, is completely based on data that was collected by himself and Tycho Brahe. So this is not a law that he formulated by intuition. Now this law, which I called one of the Kepler's laws of planetary motion, this law was not the result of intuition. It was the result of painstakingly searching and analyzing the huge data collected of planetary motion through a telescope. So this is an empirical law, and it's interesting to know that this law was developed about 7 or 8 decades before the Newton's laws came in the picture. So Kepler had given this empirical law before, and this was based on the data. He just gave a law that fits the data in the best possible manner. And then Newton, about 7 decades later, he just kept by thinking and applying his intuition. He gave these laws. This is one of the 3 laws of motion. And this is the law that corroborated Kepler's law as well. So empirical law waits to be corroborated by a theory. And that happens, luckily in this case, Kepler's law was corroborated a few years later, a few decades later, by Newton's theoretical law of F is equal to ma. Now, in some cases, you may find, yes, I'm just showing it, a theoretical example of this Newton's law of motion. An empirical example was Kepler's law of time period of a planet around the Sun. Now, as I just now said, that empirical law that's developed on experimental data may sometimes be supported later by a theory, and sometimes it waits to be supported by a theory. No particular theory comes up. For example, I can mention here that the laws of friction is, you are aware that whenever a body moves on a rough surface, whenever a body is moving on a rough surface, any attempt is made to move it, a frictional force comes in the picture at the surface separating the block from the ground. Now this frictional force is found to be is equal to a constant called coefficient of friction multiplied by normal force. That's another kind of contact force. This is a normal force given by the ground, and this is the frictional force given by the ground only. And it has been found experimentally that the frictional force does not depend on the area of contact between the block and the surface, but is proportional to the normal force, and that constant proportionality is called mu, that is coefficient of friction. Now these laws, which were developed centuries back by Amantons and Leonardo da Vinci, they are actually empirical laws. They are based on experimental data. There was no theory behind them. And even today we are struggling to find a really acceptable theory of friction because it's based on physics, chemistry and metallurgy. So yet we have to develop a proper homogeneous theory of friction that can explain why exactly this empirical law is valid. Why does friction not depend on the area of contact, and why it varies directly as normal force? That's yet not well explained, but the explanation is not fully grown. That I am trying to say. So once again, to wrap it up, theoretical laws are the work of intuition and educated guesswork of a scientist, and then is corroborated by the experimental data. On the other hand, empirical laws are developed, constructed rather, to fit the data available with an experimenter, and later a theory comes forward to justify that empirical law, and in some cases the empirical laws are yet to be established theoretically. So I was back to the topic I was trying to start earlier. The laws are not sacrosanct. It's not a physical law will remain valid throughout centuries and can never be any change in that. Nothing like this. I'd like to mention one particular instance of caloric theory. This caloric theory is the theory of heat actually. Caloric theory of heat. This was a very popular theory until the middle of 19th century. Caloric theory of heat. This theory believed that whenever a hot body is brought in contact with a cold body, say in contact with say through a conducting wire or things like that, The flow of heat is taking place in terms of an invisible weightless particle called caloric. Once again, whenever a hot body transmits heat to the cold body, that is happening in terms of the transfer of a weightless invisible particle called caloric. This theory this was developed in the 17th centuries, and it was a very popular theory which even helped Sadi Carnot to develop the law of thermodynamics, second law of thermodynamics. But at the beginning of 19th century, or rather towards the end of 18th century, Count Rumford, and in 1840s, scientists like James Prescott Joule in England and other people like Helmholtz and Robert Mayer, they raised questions about this theory. They said the theory cannot be correct. And that time the scientists have raised lots of outcries against that. Caloric theory is good, there is no need to change them. This was definitely, whenever you're going to change something, a lot of protests come because people are feeling comfortable with that. So similarly, when James Joule, Count Rumford, Robert Mayer, Helmholtz, they said that heat is a form of energy. And there is nothing called an invisible weightless particle called caloric. There are a lot of protests against that. But then eventually this theory was discarded, and today we know that the theory of heat is called the molecular kinetic theory of heat, and that says that heat is nothing but the random energy, mechanical energy of the molecules inside a body. So you see, caloric theory was discarded eventually to give away for a more scientific, more acceptable and more universal theory called kinetic theory of heat. This type of things do happen. A previous law, a previous theory discarded, a new theory, a new law comes into the picture, as we have just now seen.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.